In part 2, I will explain the interactions between ultrasound and materials. To study this part, you first need to understand what concepts we need to learn here. I'll briefly explain this, and then we'll move on to the main topic. Let's assume that there is a certain material here. Here, as the ultrasound travels along, it encounters this material. Part 2 is all about studying what changes occur when ultrasound meets this material. Let's think about this for a moment. It has encountered the material. Some of it could be reflected and go back. And some of the ultrasound may scatter in various directions. Another portion may hit here, refract, and travel in a different direction. Finally, some of the ultrasound energy here may be absorbed into the tissue when it encounters it. When ultrasound encounters a material like this, it can be reflected, scattered in various directions, refracted, or absorbed by the material. All of these situations are considered interactions between ultrasound and the material. So in part 2, we will go through each type of interaction, one by one. It's not difficult. You just need to remember what kinds of results occur when ultrasound meets a material. Let's start with the first topic, the speed of sound. As the name suggests, this section summarizes information about the speed of sound. Let's take a look at them one by one. First, the unit for sound is meters per second. Just memorize this simply. Next, there's a second important point. The speed of sound increases as the material becomes denser. Then comes liquid, and finally, in the case of gas or air, the speed is the slowest. Next, let's look at the relationship between sound, density, and stiffness. Questions about this relationship often appear on exams. I'll explain an easy way to memorize this. As you can see, the first letters here are the same. This means that these two are directly proportional to each other. Again, when stiffness increases, speed also increases. Next, the first letters are different from each other. Here it's S and here it's D. In this case, density and speed have an inverse relationship. Shall we take a look? When density increases, speed decreases. They have an inverse relationship. If you just remember the first letters like this, you can easily summarize these relationships. Next, let's move on and look at the second, acoustic impedance. It's also referred to as Z in other terms. They mean the same thing, so just remember that. When studying ultrasound, I can say that understanding this concept is the most important. That's because ultrasound images are created precisely due to this impedance. So let me first explain what this is about, and then we'll look at each part one by one. Here is the ultrasound machine. When we perform an ultrasound exam, we transmit ultrasound waves through the probe. When the ultrasound is transmitted like this, each organ reacts differently. Let's take a look. When the liver encounters ultrasound, there are certain ways it reacts. Next, the way the gallbladder reacts and the way the right kidney reacts are all different as well. For example, let's assume the liver reacts to this extent, the gallbladder to this extent, and the right kidney to this extent. So the degree to which each reacts will be slightly different. These reaction values are called impedance in ultrasound. All these different impedance signals are collected together and then sent back to the probe. When these collected signals are sent to the ultrasound machine, the images of the liver, right kidney, and gallbladder are created on the ultrasound screen. In the end, an ultrasound image is created by gathering the differences in impedance of each organ and turning them into a visual image. Now, based on this content, let's go through the explanations in the textbook one by one. If you look at the first sentence, it refers to the resistance to sound transmission. This is the basic concept of acoustic impedance, and it's okay to remember it simply as a kind of reaction. I explained this earlier with a diagram. When you transmit ultrasound to the liver reacts in a certain way. You can easily understand this reaction as acoustic impedance. In other words, the degree to which tissue reacts when ultrasound is transmitted to it, that's what impedance is. The degree of this reaction varies depending on the type of tissue. In the case of air, there is almost no reaction. So you can say that air has the lowest impedance. You need a reaction in order to create an ultrasound image. But since air doesn't react, it doesn't show up well on ultrasound images. Next, you can think of soft tissue as having a moderate level of reaction. Then, in the case of bone, it has the strongest reaction. In other words, you can say that bone has the highest acoustic impedance value. Because bone reacts the most to ultrasound, it appears bright on the image, which is a characteristic of bone. What you can learn from this is that the more strongly a tissue reacts to ultrasound, the brighter it appears on the image, and the less it reacts, the less visible it becomes. That's how you can summarize it. Next, there is a very important point. I explained this earlier, right? Ultrasound images are created based on these differences in impedance. As I mentioned before, the liver, GB, and right kidney all have slightly different impedance values. The basic concept of ultrasound imaging is that these differences are what create the ultrasound images. You are all people studying ultrasound, right? So at the very least, you need to know how ultrasound images are created. How are they made? Ultrasound images are created by collecting and displaying the differences in impedance as images. Just make sure to remember this part well. Next, there's another important point. This is the unit for acoustic impedance. The unit is a bit unusual, isn't it? So make sure to remember this unit. If you look to the side, you'll see the same concept expressed using the term rail. This means the same thing, so you can memorize them together. Next, I'll explain about ultrasound gel. When performing an ultrasound examination, this gel is used. It's important to know why we use this. This is something that appears on exams. As you can see, ultrasound gel is used to reduce impedance mismatch. Another way to put it is that it's used to eliminate air, and I'll explain this as thoroughly as possible with illustrations. First, I apologize for not being very good at drawing. I hope you'll understand. Let's assume we're performing an abdominal ultrasound examination. Then, you need to transmit the ultrasound to the abdomen using the probe. After sending the signal like this, the returning signals are collected and used to create the ultrasound image. But the problem is that there is air between the probe and the abdomen. What exactly is this air? It has a very low acoustic impedance value. So when the ultrasound encounters air, it doesn't transmit well and just disappears. That's because air hardly reacts at all. So when the sound waves you send hit the air, they all just disappear. When this happens, there are no returning signals, so you can't create an ultrasound image. As a result, to produce a proper ultrasound image, you need to eliminate the impedance of the air present here. In such cases, if you fill this space with ultrasound gel, you can reduce the acoustic impedance mismatch. By eliminating the presence of air with this ultrasound gel, the ultrasound waves are transmitted effectively. With the signals that return in this way, you can create clear ultrasound images. Let me summarize the textbook content once more. Please remember that gel is used for the purpose of reducing acoustic mismatch or removing air. Let's move on to the next topic. From here, I will start to explain step by step how ultrasound interacts with materials. First, let me explain with a diagram. When ultrasound encounters a material, various interactions can occur. First, there is reflection, where the sound wave bounces back. Second, there is scattering, where the sound wave spreads out in various directions. Next, there is refraction, where the ultrasound changes direction as it travels. Lastly, the fourth reaction is attenuation, which occurs when the ultrasound is absorbed into the material. So from now on, I will explain each of these four stages one by one. Similarly, there are specific keywords associated with each part. If you organize just these points well, you can easily understand the content. First, let's take a look at reflection. The most important keyword in reflection is that there must be a difference in acoustic impedance. This is the most important keyword. Once again, for reflection to occur, there must be a difference in acoustic impedance. For example, if the values of acoustic impedance are the same, in this case, reflection does not occur. It's essential to include the point that they must be different. If you look at the next sentence, I've summarized it here. It explains that reflection does not occur when the impedance values are the same. You can just keep this part in mind as a reference. Next, there's a second important keyword. It's when the ultrasound enters perpendicularly. As you can see, there's a material here. When the ultrasound enters perpendicularly like this, reflection can occur. This concept of angle is also closely related to reflection. You just need to remember two simple points. First, the difference in acoustic impedance. Second, the ultrasound must enter perpendicularly. As long as you keep these 2 points in mind, you'll be fine.